Statistics Unit 4, Lesson 2, One Proportion Hypothesis Testing. In this lesson, we want to learn how to test a hypothesis about a population proportion. So then the lesson before this, we looked at how to get a point estimate and turn that into an interval estimate of likely values. Another use of statistics is to decide whether a certain hypothesis about a population is true or not by hypothesis testing. The general idea is that you have some hypothesis that you want to test. We're going to translate that into two statistical hypotheses. The null hypothesis, or H0, is that some theory we have about the population is true. And then the alternative is that HA is that some other theory, or simply this one is not true. Then we're going to calculate an appropriate test statistic, which depends on the type of the data and what we're trying to test and so on. And then we're going to use the value of that test statistic and the shape of the distribution, assuming that H0 is true, to come up with whether our hypothesis is likely or not. So our test statistic, because we know it has sampling error and so on, will have a certain distribution or shape. Some of those types are normal, t's, chi-square. Some values of this distribution are more likely than others. What we want to do is, if it's a reasonably likely value under the null hypothesis, we're going to say, well, we're not going to say that the null hypothesis isn't true. But suppose it ends out in one of the low tails of the normal, where we know those are very unlikely values. If you remember, past 3 standard deviations away from the mean is an unlikely value for a normal distribution. Then we would say, well, if it ends up there, we're going to assume that our H0 is not true. Of course, unlikely values can still happen, so we could make an error when we do that. And there are really two types of errors that you can make. Alpha, which is the probability of a type 1 error, is the probability that you say reject H0, which means you're going to say H0 is false, and it turns out H0 is really true. Or beta, which is the probability of a type 2 error, when you say I'm going to fail to reject H0, which means you're not sure if H0 is true or not, and it turns out it's really false. The first type is more serious because it says the exact opposite of the truth. So you have to pick one of them to control. If you make this one small, this one will get bigger. If you make this one small, this one happens to get bigger. So we're going to choose the value of alpha. That's called the level of significance of the test. And that's chosen on how important it is that we don't make errors of this type. So we don't want to reject it too easily, but only if the data really warrants it. People, as I said, generally choose like for confidence intervals, 0.01, 0.05, sometimes 0.10, but we'll use usually the numbers of 0.01 or 0.05. Those values should be chosen before you look at the data so that you're not influenced by just what you see and you're like, oh, that one's not very far away, I'm going to use 0.05. No, it shouldn't be done like that. It should be done ahead of time. So now, based on the correct distribution, we're going to look at where our test statistic falls in terms of the distribution. Is it a likely or an unlikely value? And then we're going to reject H0. There's going to be some critical value there, and based on that value, if it's in one section, we're going to say fail to reject, and if it's in the unlikely part, we're then going to say that we reject that H0 is true. So for the proportion, we want to test one of 3 possible statistical hypotheses. They all have the same null hypothesis, which is that pi is some specified value, but they can have different alternatives. One might be, well, it's just different from that number. And the other one might be, no, I think it's bigger than that number. Or the third is, no, I think it's smaller than that number. So pi 0 is the one given in your research hypothesis that you think it could be that number. So if H0 is true, then we know from our previous discussion about estimation that if we have these conditions that ensure that our sample size is large enough, then if we put this distribution, p hat, before it was pi, but now under H0, pi is pi 0, so we can substitute pi 0 there, and the same is true for the standard deviation, that this will have an approximate standard normal distribution. So now we're going to reject H0 if p hat is sufficiently larger than this so that that's going to give a very large z value, or if it's sufficiently smaller than that so that it gives a very small value, because those values would be unlikely if H0 were true, meaning if pi is really pi 0. Now to decide on what's too large or too small is, we have to use that error level alpha that we picked. If we have a two-tailed test where we want to know if it's different, well, we want to reject now if it's too small or if it's too large. So we're going to take that alpha and split that into two tails. This one being z1 minus alpha over 2, and then we know this one's the opposite. Z alpha over 2 is the negative of that, so we just put the negative one there, just like we had in testing. And if it's anywhere in this region, we would fail to reject. If it's in one of the unlikely regions, we're going to reject the null and say that this is true. For the less than, we're going to reject for small values, so we put all of our error here. If it's up in this area, we're going to fail to reject, and if it would be less than z alpha, we would reject. And then for the right-tailed alternative, we're only going to reject for the large values, so all of the alpha would now be in the right tail, and we would have, this is now 1 minus alpha less, so that's c1 minus alpha. So this gives us a rejection rule based on the alternative that we were considering. If we had different, we were going to reject if it's less than z alpha over 2 or bigger than z1 minus alpha over 2. Of course, this one's the opposite of that one. Or if we have the alternative is less than, we're going to reject only for if it's smaller than z alpha. For bigger than, we're only going to reject if it's bigger than that number. Or we can alternatively calculate what's called the p-value of the test. The p-value is the probability that we got something more extreme than our own statistic if the null hypothesis is true. More extreme means in the direction of your alternative. So for a two-tailed test, you would look at the absolute value of yours and look at like not only whether it was bigger than that, but smaller than the negative. So the p-value would be from two tails. For less than, you would only look for the probability that it's less than what you observed. So if it was up here, it would have a very large p-value. If it was smaller down here, it would be a small p-value. And for this one now, we want to know if it's bigger than pi 0. So the p-value would only be the probability that it would be bigger than that. If the p-value is a small number, that means that our observed value was in the unlikely regions, so it would have a small probability, and then we would want to reject our statistic. So instead of having these three different rules, if we're able to find a p-value, then we can simply reject the null hypothesis if the p-value is less than alpha, and fail to reject if the p-value is bigger than that alpha. For one proportion, we can find the value of the test statistic and the p-value using the one proportion z-test, where we put in the same sort of things that we did before, only now we have to put in the hypothesized value. They happen to have called it p0, that's our pi 0, and then they want to know the proportion is different from that, less than that, or bigger than that. We would have to pick the correct alternative depending on what alternative we're testing, and then we're going to calculate that. In order to test a hypothesis, we're going to write down 7 different things. I want you to give the variable population, sample size, the statistic alpha, and any other information in the question. You're going to check if the assumptions of the test are met, which here are the n p hat and the n times 1 minus p hat being more than 5 and n being bigger than 30. You're going to state the statistical hypothesis being tested, meaning H0 and HA, give the test statistic formula and its calculated value, and then find the p-value. So you're going to give the formula, the value, and the p-value. Then I want you to give, at least for now, the rejection rule based on the alternative and also on the p-value rule, and then make your decision of reject or fail to reject, and finally write your conclusion in terms of the variable, the population, and the hypotheses in question. So we're going to look at 2 examples. We had the scorpion bite question, and I'm not going to read through all of that, but we want to test whether the true proportion with such complications was different from 0.7. So this is from the other part. We had whether or not they had cardiovascular complications. The p-hat was 0.65. We checked those before when we did a confidence interval, so we know that the standard normal approximation holds. What's different here is that the null is that we have pi equal to 0.7, or the alternative, we want to know if it's different from 0.7. So that would be HA is different from 0.7. And then Z is p hat minus pi 0 over the square root of pi 0 times 1 minus pi 0 over n. That's for the all possible samples. And now for our particular sample, what do we get? If we were to put in this p hat in here, we would get this as our Z value, and our TIs will calculate this as the probability. Since this probability isn't very small, we know that this is a likely value. Remember, only Z's that are getting close to 2, 3, those are the unlikely values. This is a very likely value, and that comes from the p-value. But the actual rules are reject if it's less than z1 minus alpha over 2, which is minus 1.645, or bigger than z, which is 1.645. Again, you can get that from here. Or reject if the p-value is less than alpha. So in either case, this isn't less than this, and it's not bigger than this, so we would fail to reject. Or if we looked at the p-value, this is not less than 0.1, so we would fail to reject. So that's our conclusion here. So we cannot conclude that the proportion of scorpion bite patients with cardiovascular complications is different from 0.7. In another example, a telephone company is trying to decide whether to add a new feature to its phone since the extra cost may keep people from buying it. The company decided to survey potential customers and to proceed only if the survey strongly indicates that more than 60% of the customers want the feature enough to pay extra for it. In a sample of 160 customers surveyed, 118 wanted the feature despite the extra cost. What should the company do? Use a significance level of 0.05. So the variable is whether or not they want that feature despite the extra cost, the population, all the potential customers that they might have. The sample size was 160, and p-hat was 118 out of 160, which is 0.7375, and the alpha, the level of significance, 0.01. In order to know whether we can use our standard normal approximation, we're going to check n p-hat, which is 118, and n times 1 minus p-hat, which is 42. Again, these are the number that wanted, and these are the number that didn't want. Those were both more than 5, and the sample size is more than 30. So we can assume that our standard normal approximation will hold. The null hypothesis is that pi is equal to 0.6, and the alternative, they said they wanted it only if it was more than 0.6, so that would be pi is bigger than 0.6. This is the formula for the test statistic. And now what did we actually observe? We observed that for this p-hat, that would give us a z of 3.550, meaning this is 3.550 standard deviations away from 0.6, and it has a p-value of 0.00192, meaning that this is now an unlikely value because it's a large z or a small p. But formally, the rejection rule is if z is bigger than the z1 minus alpha, which is 1.645, or we reject if the p-value is less than 0.05. So we would reject. Again, that's because this is now an unlikely value if pi were really 0.6. So we can conclude that the proportion of customers who want the feature despite the extra cost is actually more than this. Remember, rejecting this means we believe that this is now true and the company should go ahead with its development.